I think because these are very general talks, I will try to speak at a very general level. If I, of course, misjudge something, then just stop me and tell me that this is low level and you want something harder. So that, there is flexibility.
Good. I think that's why the questions come in then. So yeah, people are still joining a bit.
Yeah, I didn't want to make any assumptions, about these background courses and so on. I think it's okay that even if you haven't had any courses, it's okay to tune in, and maybe you get something out of it. And at least at the beginning, I will try to set the scene properly, and then, maybe towards the end, it will become a bit more technical. But, I think it will make sense, hopefully.
Yeah. Good. We're getting a lot of people today. It's great. I guess it's the first talk of the term.
I think physics is the best form of escapism. I don't know. I so highly recommend this that you have no idea. I think it cures all psychological problems for me. I'm almost like one of those religious leaders who is kind of recommending to you that this is the religion. This is it. It does it for me, obviously. I appreciate it doesn't do it for everyone, but I'm very happy that we are spending time doing this rather than something else. I think it's a very good way of doing it.
Yeah, no, I'm glad you see it that way. I like, with the reason why I'm part of the society is because I do think it's a great way to relax and kind of.
I think so.
Get a bit away from things. Of course, if your main thing is physics, then maybe it doesn't work too well. But for some people, it still does. So
yes, I feel sorry for people who don't get it. I don't know how else to put it, but yeah.
Yeah. So I'm gonna wait another minute. Usually I wait. I start looking at if people are still joining at 5 past, you might wait even a bit longer.
Yeah, I'm happy to do even. There is this continental way of kind of extra 15 minutes, allowing people to come in and so on. So I don't have anything actually for another couple of hours. So I think we can be relaxed.
Good. Meeting. I know you also you're not just a scientist, in that you're not just writing scientific papers, you're also writing books.
Yes, and I think this is an interesting challenge, how to communicate in a way that that you're understood, because when you write popular books, of course, you're communicating to probably yourself at the age of, I don't know what, 15, 16, these are the kind of books I would have loved to have read as a teenager. And then you realize that you are, of course, frequently inconsistent. So it's very funny that when your colleagues read your popular books, they kind of expect almost some kind of scientific consistency out of that, which obviously that's not what you're trying to do. You're trying to explain why something is interesting and exciting and so on. And I think somehow pleasing both of these audiences is very hard. I mean, I don't personally care about my colleagues when I talk to the general audience. I get accused of being an instrumentalist or Copenhagen or many worlds or whatever. You can throw whatever philosophy you like at me, but I'm just a physicist, so that's kind of how I take it. And I hope they're enjoyable to read. I don't know, again, if anyone is interested in any of this, and if you have any other questions during this talk, by all means get in touch, and I can send you whatever literature you want, and this includes my books as well. I can send you PDFs and all of that, so it's not a problem at all. I mean, of course, don't feel that you have to read my books. Maybe it's not your kind of thing. And I think I'm a terrible writer. I prefer talking, and whenever my lecture is recorded and then someone bothers to write a paper out of it, it sounds much better to me always than when I write it. I'm really a terrible writer, and I don't enjoy it. I'm good at writing 1 or 2 pages, but I can't be bothered to make it coherent and exciting, over 200 pages. It's not my kind of thing. I'm not doing that well at selling my own books. I understand, but
I was going to say.
Yes.
But that's great to hear. I say that after talks very often, that people don't really understand that scientists, they don't do it like when someone tells them, I'm interested in your work, can you tell me about it, or can you point me towards whatever, that's a good thing. They're not bothered by it unless you're that one professor in the department who for some reason every student wants to work with. Then at some point you kind of, but the majority of academics, they are so happy to talk about their research because that's what they want.
Absolutely, I think it is the most exciting thing you can do. I think, and most of us would probably spend a lot of time doing that if the circumstances are right. If you have an audience, that is really interested in what you're saying, I think that's absolutely right. And somehow maybe this is not quite clearly communicated. I think we scientists are usually to blame for some of this misunderstanding out there, that people don't quite understand how we feel about the stuff that we do.
Yeah. So, yeah, to any students out there listening, just ask questions, please.
Yeah, ask a question, and certainly don't be scared to say that you love physics. That's it. That's exactly what we do. It's an amazing activity, and like I said, there was a period, I don't know between what and what, but 15 and 20 in my case, maybe the age of 15 and 20, when I kind of tried all sorts of things, and you kind of think, okay, this is going to be exciting, that's going to be exciting, and in the end, physics kind of ended up being the most exciting thing I can think about, and it's kind of it's interesting, no philosophy or religion or literature or whatever else really didn't, drugs, whatever you want to throw there, it just didn't do it for me. And I understand not everyone may feel like that, but I think it is a beautiful thing that most people can appreciate if it's communicated properly,
Yeah, absolutely. So very quickly, can you have the chat open just in case people have questions? I see
the chat is open. Yes, I'm looking at it. There are no questions. I'm kind of doing this parallel screen, that I can see both.
So let's set the scene. So you're working in quantum information, and you want to talk particularly about using photons for that. So you're going to do an introduction to quantum optics.
Great, thanks a lot for inviting me. Actually, it's a pleasure to talk to you all. And like I said, please feel free to either interrupt me by asking a question directly or typing it into the chat line. I'm very happy. So what I want to tell you really is quantum optics is a very suitable topic for a physicist because it teaches you about the evolution of physics better than anything else. So the fundamentals are there, really. If you want to understand quantum field theory, quantum optics is probably the way to go. But also, technologically speaking, I'm thinking of most of the implementations of quantum computation are quantum optics. Either you're using photons or atoms or combining them. Even, I might offend a few of my colleagues in the solid state, but I think even what I see with superconductors and qubits like that is actually doing quantum optics. And maybe to pay them a compliment now, they're doing quantum optics better than quantum opticians, if you like. So in a way, I don't think it's an overstatement to bunch all of this into quantum optics. So most of you will know that we started with geometrical optics first. So that's the first classical theory. This led Newton to conclude that light is made up of particles. And that's simply because light travels in straight lines in a uniform medium. And if you look at your experiment under the right conditions, of course, which at that time was maybe the only accessible thing to Newton. So Newton had this idea that given that particles go in straight lines where they're not affected by any forces, and given that light also goes in straight lines, it's not completely crazy to suppose that light is made up of particles. And then, as you know, he had strong opposition there. There was Huygens, who kind of flagged up all sorts of interference phenomena. And Huygens said, well, it's very hard with particles to explain all of these things that we can already see, all sorts of rings, shadows, and things like that. And Huygens was very keen on waves. Huygens, on the other hand, had problem with polarization. He couldn't explain that because he thought of the wave as longitudinal, interestingly enough. So it oscillates in the direction of propagation, whereas now we know that the wave is a transverse wave. So all of these things, you know, before Maxwell had their own advantages and disadvantages. And then, of course, Maxwell wrote down his equations, and possibly, I imagine, to his great surprise, they resulted in a wave equation for the electric and the magnetic field, which actually propagated the speed of light. So he was able to completely theoretically, this is almost the ancient Greek style, you know, that you're sitting in your own study, you're just fiddling with equations, with symbols, with mathematics, and out comes something magical, which is that light is just a form of electromagnetic wave. And so in that way, optics, if you like, becomes a special case of electrodynamics. There's no reason to study optics separately from that. Now, this brings us up to the quantum side. Of course, incidentally, and I think as all of you will know, optics as a wave phenomenon had to also explain the geometrical optics. And this is always the case with science, that a more advanced theory can explain more phenomena, but in the special case, it also should be able to explain the less advanced version, the previous version. It's just that the understanding is very different. So it's not that when you take a special limit of Maxwell's equations, you will get geometrical optics, but you will still maintain that light is a wave. It's just that when the wavelength of light is very small, suddenly light will behave actually like a stream of particles. So it won't diffract, it won't interfere, and all of these things won't exist if the wavelength is smaller than the size of the aperture and so on. So even though it reproduces all the physics that was previously known, the explanation is still very, very different. And now I want to upgrade us one level up from Maxwell. And I think, as you know, most of you will know that this was clear to Einstein already. Einstein really started quantum physics, and you can say quantum optics, by arguing that photons exist, that you can't just get away with the wave theory of Maxwell, but you have to acknowledge that there are some quantum degrees of freedom there as well. And so he introduces this photon. And then he spends a long time, and it's always, you know, I say this with great satisfaction, because I always catch myself making all sorts of stupid claims that I later regret and things like this. And then when you read things, and I encourage you to do that precisely for this reason, when you read even papers by people like Einstein, the guy made mistakes left, right, and center. I mean, one year he would strongly maintain one thing, then he would completely contradict himself, and so on. So, you know, in the true spirit of science, as I was saying. So what did Einstein do? Einstein had this intuition that when Planck's constant goes to zero, then quantum optics should reduce itself to wave optics. And this is what you will be usually taught in your undergraduate studies, that h bar going to zero is the classical limit. And I'm here to tell you that this is completely wrong. It doesn't make sense. If you see a book like that, probably just stop reading it and go on to another book. Anyhow, what is my point here? My point here is that, interestingly, Maxwell's equations are completely correct, even quantum mechanically. You don't need to modify them. So not only did Maxwell, by the way, Maxwell's equations also comply with relativity. This was 50 years before relativity, but somehow, because of their mathematical structure, they are already invariant under Lorentz transformation. So Maxwell, in a way, you could argue, anticipates relativity, but because Maxwell's equations are still the same in quantum mechanics, you can kind of say he almost made the ground fertile for quantum mechanics to jump in. Let's put it that way. I wasn't going to say he anticipates quantum mechanics, because of course he didn't. There was no experimental evidence at that time. So what do we do in quantum mechanics? And this is the interesting thing. So Maxwell would say, at every point in space and at every instant in time, the electromagnetic field has to be described by 6 numbers. There are 3 components of the electric field, and there are 3 components of the magnetic field. And so it's very hard. Of course, it stretches our imagination. You know, people always say, how do I imagine something like that? The space-time, each point of space-time contains a different sequence of 6 numbers that then change from time to time at all of these different points. And magically, like I said, they comply with relativity. So what Einstein didn't know, Einstein thought, I have to add an h bar term to Maxwell's equations, and then when h bar goes to 0, I will recover the classical optics, if you like, wave optics. And that, like I said, was completely wrong. The thing you must do, and we know that now, is that you must upgrade these entities from being numbers into being operators. And I will give you a little bit of intuition how people arrived at this. And the reason why I think this intuition is interesting is because that's something we are now trying to exploit when it comes to gravity. I think most of you will know that gravity has not been quantized in a way that's as satisfactory as light, which is why I think understanding quantum optics is really a good prerequisite if you intend to do even quantum gravity. So basically what quantum mechanics says is that each of these entities, electric field in the X, Y, and Z direction and magnetic field in the X, Y, and Z direction, are actually operators. They are quantum mechanically at the same level mathematically as the position and momentum operators in ordinary mechanics. So the same way that you have to acknowledge that you cannot measure a position and momentum of an electron at the same time, you cannot also measure the electric component and the magnetic component of the field simultaneously. That's the way to go. So your elements of reality, this is something you will hear people debate all the time in quantum mechanics. What's the world made up of, actually? And you can see that the ontology, you know, as a philosopher would love to say, the ontology here is that at every point in space, I have 6 operators. By the way, these are infinity times infinity matrices, each of them. It's really crammed in terms of information. And in fact, you will hear lots of people complain that this is way too much stuff at every point in space. So in fact, I'm already preparing you for the next revolution, since I'm progressing from geometrical to wave to quantum, but maybe this description is also telling us that we should go beyond that, and it doesn't make sense to cram an infinite amount of things into a single point. Anyway, that's the way it is at the moment, and I'm just telling you how we understand it now. So how did people come to this conclusion? And for this, you have to blame people like Heisenberg, people like Niels Bohr, who thought a lot about these field measurements. And the argument is stupendously simple. And it's always nice when you have the hindsight, like we do, to look back and to kind of even feel a little bit superior to these guys and say, how come they didn't see it like this? It's just an obvious thing to see. And the obvious thing is the following one. If you have 2 charges, so let's say you have a negative charge, an electron here, the way that Maxwell introduced the field is really to get rid of this Newtonian action at the distance. So if you have another charge sitting further away from this electron, the question is, how quickly will this charge respond to the field from that charge? And Newton would have said instantaneously. And Newton was aware that this was a problem, actually. He thought about this within gravity, not within electrodynamics. But he knew that there shouldn't be action at the distance. He just wasn't sure how quickly this influence should propagate. So the way that Maxwell deals with this is Maxwell says, if you move one of these charges rapidly away from the other one, then the field here should be smaller because it's further away, but it will take the speed of light time to get from this new position to that position. So the way he does it, the way he complies with causality, is that he says as soon as the charge moves, it makes waves around it locally in this thing called the electromagnetic field. And this wave now propagates at the speed of light and ultimately reaches the position of this test charge that's testing it. And that's the whole point of the field, that the action is not instantaneous. And this is all fine and well with classical mechanics. And now I want to tell you what Heisenberg would have said. I think I'm caricaturing a little bit. He didn't quite say, he should have said it like this. I don't know why he didn't say it like this. Schrodinger said it like this, really, but in a different context. The question you want to ask yourself is this: given that I know that particles can be in superpositions of different places, what does that imply for the field that they generate? This is a very simple question. So if instead of having an electron in one place, I literally put this electron in a superposition of two different places at the same time, what does that mean for the electromagnetic field? And I think those of you that have done even the first year quantum will know what's going on. Each of these locations will independently, if you like, generate its own electromagnetic field. So if the charge is here, you will have a certain electromagnetic field on the test charge. I'm kind of assuming that they repel each other to the kind of leading order of approximation here. And if the charge is here, then this charge would respond differently. It would start to accelerate in a different direction. And now I'm going to use the standard Schrodinger's cat logic. Every experiment in quantum mechanics is just a version of Schrodinger's cat experiment. There's no other experiment at all. And I think once you realize this, it's a really nice thing to think about. So basically, given that this charge is in a superposition of being here and here simultaneously, that means that the field here is pointing in one direction and the other direction simultaneously. Both of these exist. It's exactly like Schrodinger's cat. When you couple to a superposition, you yourself must become part of that superposition. So what's the prediction here? And that's interesting. The prediction is that this charge will simultaneously accelerate in one direction and in the other direction. So if this first charge that generates the field sits here, then the test charge will go this way. But in this branch of the quantum superposition, it will go in this direction. It becomes entangled. So actually, if I measure where the charge is, the test charge, I can tell you immediately where this source charge is. And that's really interesting. And that's an inescapable conclusion if you want the interaction to be mediated by a field in between. The field has to be fully quantum mechanical. There's no two ways about it. And actually, some of you will know that Chiara Maletto and myself have kind of upgraded this argument to gravitational field. So I claim gravitational field has got to be quantum mechanical in the same way. Now, unlike with optics, no one has done that experiment with gravity. It's much harder to put a mass sufficiently large in a superposition. But with these kind of things, we do it all the time. In fact, it's become so simple that David Lucas, that some of you will know, a colleague of mine in physics department, literally gets up in the morning, goes into the lab, and does a controlled NOT gate with his 2 ions in this way before he even has breakfast. Then he has breakfast, you know, he brushes his teeth and so on. This actually is such a standard bit of quantum technologies now that anyone who is sufficiently advanced in their laboratory can perform a controlled NOT gate between 2 systems that are electrostatically charged. I'm getting, sorry, now I was too concentrated on what I was saying, and I'm gonna just spend a few seconds answering some questions. There's a question, can a single photon be amplified? Great question, actually. And yes, there are amplifiers. You just have to be very careful with what you mean by amplifying. So this explanation here at this level, you don't even really need to explain things directly at the level of a single photon. And that's one comment that I'm gonna make. What you cannot do quantum mechanically is you cannot copy the state of a photon, if you don't know it, exactly into another photon. But if by amplifying, you simply mean that I inject certain photons into a material, certain number of photons into a material, and I get more out of it, then that is perfectly possible. But you cannot clone the state, because that's one of the limitations of quantum information. And I think someone is kind of answering that question for me, which is very convenient as well. Another great question, in fact, I have a paper on that, funnily enough, is whether the same logic would apply to neutrino oscillations. And the answer would be yes, because the idea there is that you have 2 neutrinos of different masses, which are quantum mechanically flopping between these 2 states. And everything I said here about superposition being able to entangle itself to the environment, whatever is in the environment, would be true for neutrino oscillations as well. Neutrinos, as you know, unfortunately, are too light for us to be able to get anything interesting gravitationally speaking. But it did occur to me that this could be one way of testing some ideas, at least potentially, in quantum gravity. There is another question here, which says this probably goes this goes more in the direction of the measurement problem, as people call it. I don't think there is such a thing as measurement problem. I think quantum mechanics is perfectly consistent. But let me state the question. The question is, and I think this is what some people in the field would call Wigner's friend. The question is, where does entanglement stop? And this is exactly the question that Schrodinger asked. He said, if I have an atom that radioactively decays, and then the cat becomes dead and alive as a result. So when the atom decays, the cat is dead. When the atom doesn't decay, the cat is still alive. And then I enter the room and I observe the cat. Then I become entangled to this, because in one branch, I'm going to see the atom decayed and the cat dead as a result. And in the other branch, I'm going to see the opposite of this. And actually, if you follow this logic through, entanglement never stops. There is a way of describing the world without ever terminating this entanglement. And actually, that's what I'm kind of saying happens here. And I think that's why the question was there. If you extrapolate this and you keep coupling things to one another, if I add another charge here, it's also going to couple exactly to this kind of quantum mechanical state. And that's the way it is. And actually, all of our experiments so far have confirmed this. Some people, of course, doubt that this will continue like this, and that in the macroscopic domain, maybe it will stop at some point. So I think this is a great point, and definitely something to experiment with. Now, what I want to say is what is the limit to go into the Maxwell's equations then? If I'm telling you that this logic here suggests that the field in between also has to be able to be in many different states at the same time. If this wasn't the case, you could never mediate entanglements between charges in this way. So then what does it really mean? What it means for these numbers here in Maxwell's equations is that they have to acknowledge the existence of these superpositions. And I'll show you mathematically in a second how this works. But what I want to say is that the consistency with Maxwell's equations, it's not h bar goes to 0, but it's the fact that these operators give you such large numbers when you take the expected values in some quantum states. You get such a large amount of the electric field and the magnetic field that the tiny fluctuations due to the existence of individual photons become irrelevant. So what I want to say is that the classical limit, strictly speaking, does not exist. Everything is the whole universe is quantum mechanical. Classical physics makes absolutely no sense. It does not exist in this picture. But what does exist is that in some approximations, you are not making a big mistake if you just use classical numbers for your electric and magnetic field. You're not going to make a mistake because the presence of single photons, the effects of individual photons, the uncertainty I'm talking about is really not relevant at that level. But it's important to know that it's not the h bar going to 0 that gets you there. It's nothing. Maxwell's equations don't have Planck's constant in them. It's nothing to do really with Planck's constant in that way. Let me say a little bit more now. So what people like Heisenberg realized very quickly, and I think it was again Schrodinger who did this first. Schrodinger, Dirac then. I think Dirac took it really seriously, and there was another guy called Jordan who did more or less the same thing, actually. But what they did is the following. The energy of the electromagnetic field in a certain volume, I'm going to be super sloppy. I'm going to be missing all sorts of constants there. And if it makes you feel any better, this is really how I calculate. And then I just add the right constants to get the things dimensionally right. And magically, you're almost always to within a factor of 2 or pi within the right answer. So the energy of the electromagnetic field in a certain volume, the density, if you like, of energy, goes as electric field squared plus magnetic field squared. This is the energy density. If you integrate that over the volume, you would get the total amount of energy in a given volume. And I think those of you that have done Maxwell's equations, you would have done this pointing theorem and energy conservations. I think you would have seen an expression like this. Now, what's interesting, and this is how physicists work, we're extremely opportunistic. We're just looking for things that we can recognize from our previous studies, even when we don't quite understand what it is that we're trying to do. Here, you're saying, wouldn't it be nice if instead of E, I'm writing P, and if instead of B, I'm writing X, P and X being the momentum and the position of a particle. Why is this nice? Because this is called a simple harmonic oscillator. By the way, that's just about the only thing we know how to solve in quantum mechanics. And isn't it nice that everything ultimately ends up being a simple quantum harmonic oscillator? Somehow this is either a great stroke of luck or God, I think, was having probably a lot of fun when he was setting up the universe in this way that we can comprehend it at this level. So what I'm saying now is that if you recognize that the operator that should correspond to the electric field should look like the momentum operator, and this magnetic field should look like the position operator, it's suggestive because once you figure out that they don't commute, then you might as well see what happens if you put them that they don't commute to the same degree as the charges that produce these fields. This is very intuitive, actually, and clear that you should proceed this way. And so if you now, again, I'm leaving all of these things for you to really check. If you now make P proportional to A minus A dagger, and I think again, quite a few of you would have seen this in your maybe second year quantum mechanics, and X is proportional to A plus A dagger, A and A dagger being the annihilation and the creation operators. So they have a very different meaning in what we are about to do. They are not the position or the momentum of anything. What they really are the electric and the magnetic field components, and these operators create and annihilate photons. So somehow by this logic, you've managed to reconcile quantization of the electromagnetic field with these very early ideas of Einstein and Planck and Bohr and so on. So if you do this, you will know that this quantity here in the quantum mechanical version will actually end up being h bar omega A dagger A, which is the number operator plus a half. So what you're gonna conclude is that for every frequency of light is going to look like a simple harmonic oscillator. And maybe here, if I draw quickly one of those things, that another thing that we can luckily enough solve analytically is some kind of infinite potential well. If you put two very strongly reflecting mirrors and you create a vacuum state in between, and you ask yourself what kind of frequencies of light can exist inside, then I think most of you will know that when you set the boundary conditions and you have the wave equation there, Maxwell's equations, if you like, you will get a very low frequency, a large wavelength, if you like. This is the lowest mode, if you like, that can fit into this. And then the next one up looks like that, and so on. And what quantum mechanics now says, it's a very simple picture of the field. It says each of these frequencies is an equivalent quantum mechanically of the simple quantum harmonic oscillator. So that's ultimately all quantum optics is about. It says at every frequency, you can have any number of photons in principle. So what's interesting, I want to take you to the extreme quantum level, where at most we have one photon. But things are even exciting when we have no photons, and that's maybe something I want to tell you about. So in this last bit, I want to kind of maybe bring you up to speed with some of the experiments that we are doing and that I think are interesting in this context. So basically, in an empty cavity between two mirrors, what quantum mechanics says is each of these different frequencies, and they can get larger and larger. As you can see, there could be a frequency like that, and there's no limit in principle how large this frequency can be. But each of them could contain no photons, that would be the vacuum state, one photon, two photons, or any superposition of photons. And that's the most general description. So for every frequency inside, you just have to tell me how many photons are present at that frequency. And that's the full quantum mechanical description for you. And it fully takes into account the fact that you cannot know the electric and the magnetic field components simultaneously. That's exactly where the uncertainty principle leads you to, and it leads you to conclude with this logic that photons exist. Photons are really a manifestation of the fact that the E and the B field do not commute. And that's very interesting. So now, you may say, well, can anyone do anything with this? And in fact, yes, people can do it. And I can think of at least 6 Nobel Prizes so far on people fiddling with this kind of stuff. So there is this colleague of mine, Serge Roche in Paris, and you visit his lab, and he has a cavity of this kind, and you say to him, Serge, I would like to have 7 photons with a frequency of whatever, optical frequency or whatever frequencies he works with. And he's going to produce exactly 7 photons for you. He can produce any number of photons really that you like. And these were really the first experiments. By now, this is maybe 30, 40 years old technology. These are the first experiments that really did quantum state tomography on single photons and optical field right at that level. How does Serge do it is the question. What he does is he takes an atom, and I'm drawing only 2 levels of this atom which are relevant. Electrons would normally sit in the lowest level. What Serge does is he shines laser onto them to excite the electron to the upper level. And then he shoots this excited atom through this cavity. And he times the speed of the atom. So this is a very complicated, I'm giving you a kind of Mickey Mouse version of an extremely complicated experiment. But basically, if you tailor this, if you time it properly, then when the atom is inside the cavity, it will de-excite, the electron will go down to the ground level, and it will deposit 1 photon exactly into one of these modes. So he can take an empty cavity, shoot an atom through, and as the atom comes out, he's got 1 photon for you. And then you say, Serge, can you make 2 photons? Actually, I prefer to have 2 photons. He says, no problem. I'm just going to send another excited atom in the same way, and it's going to emit here, and the emission is going to be deposited directly into this. These are revolutionary experiments. And of course, now we are using them really as a piece of quantum technology. We are hoping we can scale this up to make a large-scale quantum computer. But it's beyond doubt that the electromagnetic field at this level behaves this way. Now, one thing I want to actually now emphasize, maybe that's the last bit, are some of these extremely stunning conclusions that you have here. And actually, lots of them are, to us, still work in progress. If I'm honest about it, because we don't really understand fully what this is telling us. So what's interesting when we look at this sequence of harmonic oscillators, the thing here is that even if you have no photons anywhere in the cavity, that would mean quantum mechanically that this term here is 0 on average. So the expected number of photons is really 0 in the lowest energy state. What quantum mechanics still says is that every frequency still gets half h bar omega, half Planck's constant times the frequency of energy. And this is something that's called 0-point energy, vacuum energy. It's got all sorts of names, but it's the residual energy that's frequently giving us lots of headache, but we know it's for real because it's got experimentally observable consequences. But we don't quite understand all of the consequences of this thing. So the amazing thing is that, because remember, you have to sum up over all frequencies that are present in this cavity, and there is no upper bound. You can make the wavelength as small as you like, which means the frequency as high as you like. When you sum this up, this 0-point energy that exists without any photons around, you will get something that goes to infinity, diverges. It's just an infinite sum. And actually, the way, of course, we physicists treat infinite sums in all sorts of ways. For some purposes, when this is not relevant, I tend to just disregard this. Of course, mathematicians laugh at us. They're saying you're throwing away an infinite amount of energy. But actually, in many cases in quantum mechanics, this really is irrelevant. It just reduces to an overall phase. But we do know it's real because it has manifestations, and I'm going to tell you about a few of them. Actually, I'm going to focus on one of them, which I think is interesting. This has consequences. Of course, what you're going to do ultimately is you're going to come up with 2 infinite quantities. The way this works mathematically is you're going to come up with 2 infinite quantities whose difference becomes a finite number. And Casimir was the person to realize this. Actually, it's called the Casimir effect. He said, if I really have two mirrors, in this case, you can think of them as conductors, which are perfectly reflecting, at least in certain range of frequencies, and you have the vacuum in between, Casimir noticed that the energy, if these mirrors are slightly closer to one another, is slightly smaller than the energy previously when they are further away. Like I said, you have to be very careful with these arguments because both of these energies are infinite. But as you subtract these two infinities, you miraculously get a finite number. And when you differentiate this energy with respect to distance, you will get a force. So Casimir predicts that two conducting plates, even in the complete vacuum, there are no particles, no photons around, will still accelerate towards one another. And the explanation, mind-blowingly, is because of the quantum vacuum. It's because there is still residual half h bar omega energy there. And this is interesting. When you throw away this energy, sometimes people say, oh, it's only because we care about relative energies. But one thing I want to sneak in is that when you're doing gravity, gravity cares about the absolute energy. Actually, in Einstein's GR, this kind of vacuum energy is problematic. We don't know what to do about it if the universe is full of this kind of stuff. The question is, does that really have some effects? And you will see all sorts of speculations out there in cosmology. We really don't know what to think about it ultimately yet. Another thing that people have confirmed with the vacuum is something called the Lamb shift. They looked at the energy levels inside the atom, and they noticed that some of these energy levels are shifted due to the coupling with the empty space, but quantized empty space, if you like. So basically they realized, and Lamb was the person who did the experiment and the calculation actually, he realized that these energies will be slightly shifted if the electromagnetic field was really quantum in this way that's suggested by this kind of quantization. So we now know that this is for real. And finally, this is the final thing I want to say before I really conclude with a fun example, I suppose. I mean, there are many examples I can conclude with. Is the following: if you when you learn to solve the Schrodinger equation for whatever the hydrogen atom, you would have learned that there are energy levels there. You get the lowest energy. I mean, even when you do the kind of pre-quantum Bohr's model, you will have more or less a similar picture of that. You will have a low energy level, then the next one up, and so on. And what you will learn is that you obtain this by finding the eigenvalues and eigenvectors of the Schrodinger equation inside whatever the potential it is that you are solving. In this case, Coulomb potential for atoms. And eigenstates mean that they don't change with time. So if you trust Schrodinger, what Schrodinger says is that if you put an electron in the excited state, it should stay excited forever. It should never emit a photon by going down. And I already told you this is wrong. Otherwise, Serge Haroche would not have a Nobel Prize in physics. How did he do it with these excited atoms? How did he know that they would deposit radiation when they are inside the cavity? And you can already see probably the answer. This is not the complete picture of atoms. Atoms, like everything else, are always sitting surrounded by the quantized electromagnetic vacuum. This is inescapable. It's just everywhere around us, and it permeates space-time just like any other field. So if you acknowledge that, then interestingly enough, this interaction between the vacuum and the excited atom is what leads the electron to go down and emit a photon. So whoever tells you that spontaneous emission is spontaneous is making a mistake. I know that we use this language because of historical reasons, but actually what I want to tell you is that there is no such thing as spontaneous emission. Everything is stimulated. It's just that in this case, what this is stimulated by is the vacuum state of the quantized electromagnetic field. So, you know, if you come with a classical frame of mind, you will never be able to understand spontaneous emission. It makes absolutely no sense. How can that happen? And actually, the quantum mechanical vacuum solves that problem. And I'm going to just very briefly show you that because it's going to lead me to the experiments that we are doing, actually. So the experiments that we are doing is trying to make a dead and alive bacterium at the same time. And that's actually what I want to tell you. I can't do it with cats, but I'm hoping that, well, actually, if anything, I would love to do it with coronavirus. You know, it would be a fantastic revenge for the stuff we are going through now. But you know, some people are sometimes debating whether viruses are alive because they don't have their own reproductive system and so on. So I think when we are making these decisions and we want to shut all sorts of philosophers up, you know, there are some people out there who think that life contradicts quantum mechanics. And I think what I want to show you are kind of very interesting experiments that we can already do in that direction to show that actually probably there is no clash between life and quantum mechanics. If anything, probably the opposite is true. But what I want to tell you very briefly is how does quantum mechanics describe this? You would literally write a quantum state for both your excited atom and your electromagnetic vacuum state. And what would happen when this atom spontaneously emits is that the state you would create, and now you already know that because that's how I motivated the quantum optics lectures, is that this state would go in an entangled state, which I hope you can see, where with some amplitude, this changes with time, the amplitude, with some amplitude, the atom still stays excited and the field doesn't have a photon in it. But with the rest of the amplitude, the atom goes down to the ground state and suddenly one photon appears in the field. And it's exactly this kind of flopping of excitation between the atom, which gets de-excited, and the field, which then gets excited. It's called Rabi flopping for obvious reasons, that the energy flops. And of course, it's basically what you would call a NOT gate if you are a quantum computer scientist. So this is why the presence of the quantum vacuum allows an excited atom to actually emit a photon. So that's very interesting. Why is that interesting? That's interesting because I'm going to connect it to this lamp shift, if you like. And then I'm going to tell you about bacteria. If you have an atom which could be in the ground state and excited, and then you have light, which, like I said, is a harmonic oscillator. So this is the ground state with no photons. This is the first excited state with one photon. Higher up are higher states and so on. That's basically what quantized field ultimately is. What is interesting is that if you make this frequency here the same as the energy gap between the excited and the ground state, this is something when these two systems would couple most strongly, if you like. So you would exactly de-excite the electron, excite a photon. If you wait a little bit, this photon would go down to the vacuum state and your atom would get excited. If you keep them in a close, confined proximity, and they would go back and forth. But what this means is that the energy levels of this guy are changed due to the coupling with this field here. And actually the right energy levels now are excited 0 plus minus ground 1. And these energy levels have a slightly different energies to these. They will be basically split. This is known as the vacuum Rabi splitting. So if you're measuring the energy levels of this system that couples to the quantum light, you will notice that the energy levels have a certain structure within them is not just a single energy level, but you will see a splitting here that's actually proportional to the coupling between your atom and the light. And again, this is a purely quantum mechanical effect. I'd like to call this a funny kind of an atom. It's an atom, a molecule, sorry, that's made out of a material atom, a real atom, and an atom that you can think of represented by the electromagnetic quantized field. So it's not just that quantum mechanics explains how two atoms can come together to create a molecule, but in this case, you have a very funny molecule because it's half material and half light. And that's actually what this picture gives you. So now what we tried to do, and actually the first set of experiments confirmed this, is we literally found two levels of a bacterium. So what was exciting there? We did this kind of experiment, but with a bacterium that's alive. And I thought this was fun. I actually suggested it in a state of being completely drunk with a friend of mine, Dave Coles. He was here at Oxford at that time. He went to Sheffield afterwards. A great experimentalist. And actually, I was getting more and more drunk, and I was giving Dave, I thought, more and more outrageous ideas. And every time I would suggest something, Dave would say, well, maybe I can do that too, which was hugely exciting to me. You know, how far can you really push this kind of thing? This was in the Royal Oak, but by the way, in case you're wondering, in the good old days when we used to go to pubs. Anyhow, what happened here is that the two levels for the bacterium that are relevant are exactly the ones that are relevant for photosynthesis. This is a photosynthetic system. And what happens is that light gets absorbed at a higher level, then it decays within the bacterium. And when it gets to the ground state here, the energy that's released triggers a kind of energy cycle in a bacterium, ATP kind of cycle, that actually gives energy to these bacteria. And they're extremely efficient at this. And for a long time, people debated, how can this be so efficient? And I think now we think that there must be some quantum magic, if you like, going on there. So what we thought, the first experiments we did is really to observe this kind of splitting. And it was very interesting because we observed the quantum mechanical entanglement between bacterium and light. At the same time, this bacterium was alive. And that I thought was phenomenal, because in the early days, people like Niels Bohr, and you can read some of his early lectures, were even claiming that you're not going to be able to confirm that a system is alive and quantum at the same time. You know, Niels Bohr was crazy enough to see complementarity everywhere. And I think this was one of those instances of complementarity in his case. Either you're going to be able to do physics with a living system, but it's going to have to be dead, unfortunately, or you're going to have to be able to exploit its living things, but then you're probably not going to be able to understand the nitty-gritty. That's what Bohr believed. Well, I can tell you he was completely wrong as far as this is concerned. And what was interesting to us, this is the final thing to say, is can you really change these levels through quantum entanglement in a way that the bacterium becomes more efficient at photosynthesizing? And also, can you detune it the other way so that the bacterium becomes less efficient? This would be a quantum kind of homicide, but you don't call it homicide, it's a bacterium. So it would be a quantum way of killing a bacterium to couple it to the electromagnetic vacuum so that the levels shift so much that it is no longer capable to do photosynthesis. And then, of course, immediately when you have these ideas, you're thinking, why don't I do both at the same time? Why don't I detune it one way and the other way simultaneously? And why don't I create the Schrodinger bacterium in this way? So I'm just giving you a little bit of a flavor about, regarding the direction in which we would like to go. These are still extremely difficult experiments. No one has done that. We'd like to entangle two bacteria, use them as qubits and all sorts of things just for fun. I can't actually see any obvious technological application other than maybe improving photosynthesis in this way. But I think these are fun experiments, and we're pushing quantum mechanics into the macroscopic domain. The idea really is is quantum mechanics a universal theory? Will it survive everything? Will it survive gravity? Will it survive life? And my bets are on yes, but it would be interesting really to see whether there are any limitations. So I'm going to stop here, and I'm going to look at the questions as well. But please ask me more questions if you have, because there are many things to be said about these topics. Thank you.
Thank you so much for the fun talk.
Thanks a lot.
Yeah, I mean, I guess we can start with the question in the chat. And then
yes, I can see that one question is this very important question about single photon sources. This is something that people are still working very hard at improving. In fact, Tristan Faro, the senior postdoc that I mentioned in my group, his main motivation, his PhD was actually in Cambridge with Toshiba. And I think his main goal was to produce as clean single photons as possible. The question really is one of efficiency rather than whether this is possible. The reason being that we know of a very, very inefficient way of producing single photons, which are pretty clean, and it's a process called down conversion. So it's a nonlinear process where you shoot laser light into a crystal, but the crystal every once in a while can produce 2 photons simultaneously, and they happen to be entangled. And what people do then is put a detector in the path of one of these 2 photons, and when they get a click there, they know that the other photon is shooting off in the other direction. So this is called heralding in the field. Basically, what you're doing is you're wasting one photon and absorbing it in order to trigger a preparation, if you like, through quantum entanglement of another photon. But if you get a click in your detector, you can guarantee that the other photon exists. But this is a horrendously inefficient process. So what people really want is something where you can press a button, molecule gets excited, and out comes deterministically a single photon. And we still don't have that.
I'm just seeing we're getting some coronavirus questions. Please, this is a physics talk. Refer to the NHS for any help.
Yes, I thought this coronavirus was kind of, it reminded me on one of my slides when I was giving a presentation. I don't remember who was there actually in the audience, but I put a picture of a virus inside the cavity, and then I just realized that it looks, I guess all of these viruses look very similar, which is how these vaccines work, I guess. So I kind of realized it looks very much like coronavirus, and I thought it would be a kind of a fun revenge to put a coronavirus in a superposition and dead and alive and so on. I don't know, it's just for fun, really. There wouldn't be any purpose to that.
All right, but yeah, please do ask the NHS if you have any questions.
Yeah, absolutely, yeah. Yes. There is another question. I'm just going to read them out if you're okay with that. There is a question about Landauer's limit, which is actually a great question as well. The Landauer limit is the limit which says that this is a really deep question, in fact, and it's not clear that I will give you a satisfactory answer. It's not clear that we have one, really. But Landauer said that the minimum amount of energy or heat, strictly speaking, you have to waste per gate is kT, K being Boltzmann's constant, T being the temperature at which you operate, kT log 2. So basically, Landauer said whenever you flip a bit, even when you do a NOT gate, you actually have to expand a certain amount of energy, which sounds intuitively clear to us that our computers heat up as they operate. And you can say maybe at some fundamental level, there is a limit to how frictionless you can even make them. And that's known as the Landauer limit. Now, a person called Charlie Bennett came along then and said, well, it's not clear that that's true, because even classical computation I can make fully reversible. So Bennett said, the reason why you think that you have to waste heat on gates is because your gates are intrinsically irreversible. So for instance, you have this typical AND gate where you have two logical bits coming in and only one logical bit coming out. And so Bennett would say, clearly, the logic you are using is irreversible, which dictates the underlying physics to also be irreversible. And that's where the friction comes in. And so Bennett gives a whole model for reversible classical computation. It's fantastic. It's actually exactly what I was using at the beginning when I was, like yourself, an undergraduate, and I started thinking about these things. Bennett's papers were actually the easiest ones to adapt to quantum computation because he already introduced all the reversible gates. And because quantum mechanics, as you know, the transformations on a closed system are unitary, they are fully reversible, they are as easy to make in one direction, I should say, at least at this simple level, as going backwards, then this reversible logic is the right one. And when people talk about quantum computation, they say that it's ultimately frictionless for that reason. So actually, Landauer's limit may not apply here. And maybe we can do the full computation without ever wasting any energy or heat. You know, if you are environmentally minded, this sounds fantastic, actually. You know, this exactly is something we should be aiming at if we are trying to reduce kind of pollution and things like that. We are very far from the Landauer limit, by the way, the current technology. The current computers probably use tens of thousands of KT log 2 per bit of information. We're very far. The DNA uses 100 per base. If you think of base pairing in the DNA as your logical gate, then nature is about 100 times more efficient than our conventional computers. But if you extrapolate this logic and if you say, what if we had a fully fledged quantum computer, fully reversible, then it seems to me you'd be able to beat the Landauer limit. And that sounds very interesting to me.
I see there's a question about philosophical questions of quantum mechanics. You can talk about that if you want. You mentioned earlier. We had a talk a while ago that's on our YouTube channel, all about the philosophy of quantum mechanics, where James Reed talks about his take on all of them. So he introduces them and his thoughts on it. I thought it was a really good talk. I'm going to put the link to our YouTube channel in the comments if anyone wants to look it up. But feel free to comment on it as well.
It's great. I think it's a nice point because, like I said, it's really going in this direction of testing. Again, I know when people say many worlds, the objection is frequently more to do with maybe semantics or certain other psychological issues even, rather than, that's why I would rather use something like macroscopic quantum mechanics. You know, does quantum mechanics also apply to macroscopic objects? And my answer to that would be that we know that this is true up to a certain level, of course, experimentally. We don't know it beyond this level, and it's really worth testing it. But I don't think there is any contradiction with quantum mechanics being assumed to be universal. So that's kind of a cautious way of putting it. I think the trend of what we do is in that direction. It's just that really, if you want to fully test things like when I make an observation, you know, ultimately you're going down the Schrodinger cat experiment, like I said. And what you really want to be able to show is that even after you made a measurement, you are still, I mean, when I say you can see this is loaded with all sorts of grammatical problems, and quantum mechanics is really giving us headache because we are used to some kind of classical logic and grammar. So basically what quantum mechanics would say is that there would be a version, a copy, whatever you want to call it, of you, which exists in one branch of the superposition, which sees one outcome, and there is a copy which sees another outcome, but both exist in a superposed ground state. Now, what needs to be tested there for this to be confirmed is that each of these copies of you needs to see a definitive outcome. And I think the claim here is that that's what happens. Each of these copies knows, one of them sees a dead cat, the other one sees an alive cat. No one sees anything fuzzy. Quantum mechanics doesn't say, you know, it's like being drunk. It's not like being drunk at all. Maybe when you're popularizing science, you tend to use this language. There's nothing fuzzy. Every entanglement between the observer and the observed results in a definitive state of each of these. It's just that quantum mechanics says both of them exist in their own respective universes. Now, the difficulty of testing this is not what I said to confirm that they see a definitive outcome, but to interfere the two possibilities. And that's the difficult bit. So it's like every quantum experiment, you need to make a superposition of your particle, and then you need to bring it back to see whether this superposition produces wave-like interference. And that's what quantum mechanics says. And when it comes to macroscopic objects, it gets harder and harder to superpose them and then to reverse this superposition. So to me, this seems more like a technological challenge. But if you really proceed on paper and you really analyze the thought experiment, it seems to me there is absolutely no contradiction with quantum mechanics, which of course is not to say that it won't fail. It may fail, but I think the way it's going to fail is that it will lead to something probably even more mysterious, if you like, rather than some return to classical physics. I think it's highly unlikely that it will collapse and become classical in that sense. Like I said, I can say much more, but maybe I should just look at some other comments to give everyone a chance.
Some kind words from Maria. Thank you. Thank you for enjoying it.
Thanks a lot. Yeah. Again, this reminds me, these coronavirus questions are interesting as well, because one of the people who's funded my research is a private individual, actually, and I think she's given us a lot of money just to play around with these kind of crazy ideas. The concern was exactly with this, you know, the question was, oh, if you put a virus in a superposition, you know, is it going to become even more potent and so on? And like I said, all we do at the level, yeah, it's funny, all we do at the level so, you know, this is like a many worlds kind of terrorism in a way, you know, creating an even more potent virus in all the worlds, whatever, you can, you know, you can kind of extrapolate yourself. But the bottom line here is that what I'm trying to test really are all of these claims that something will fail when you take quantum mechanics outside of its comfort zone. So when I'm thinking about a living system, I simply see it as a very complex set of different energy levels that I can excite. So for me, a bacterium is no different in that sense to the hydrogen atom. I just need to be able to identify the right energy levels. And as long as I can tune my photons exactly on resonance with these transitions, Bob's your uncle. You know, you can just proceed and couple these energy levels in the same way. And I think someone here mentions exactly that. Someone says, are you actually using these bacteria as qubits? And I think that's it. I'm really pretending that all of the other complexity is irrelevant for these experiments, and I'm just thinking of them as two-level atoms. Of course, the fact that they're alive and that you can see them move about, you can see actually that they maintain their integrity of being alive during the experiment is just very interesting, precisely because of some of these early philosophies. I think maybe you would not be surprised to hear names like Wigner, von Neumann, even Einstein at some time maybe would say things like, when you make an observation that collapses the wave function, that's actually when quantum mechanics becomes classical. And I think that's the wrong way to think about it. In fact, Schrodinger was right about this as far as we are concerned, which is, it's not that the observer makes the system classical, it's that the quantum system makes the observer quantum. a superposition, to use the virus analogy again, a superposition is like an infectious virus. As soon as you get in touch with the superposition, you yourself become superposed. I think that's the right way to think about it. And actually, it's an interesting way of understanding the universe as a kind of an entangled web of kind of observers and the observed, which are completely symmetrical in this picture. But I think my point is, let's just push it as far as we can, and let's really see whether we can detect quantum properties in all of these complex systems. I'm hoping that my friends in neuroscience will one day join us in this, and that they will really be able to even play games with our perception and try to do experiments that may reveal some quantum effects there. You know, if I was a young scientist like yourself and I was thinking, what shall I do, you know, in the 5 years or so, I'd be jumping on crazy questions like this. You know, this is going to define science for the next 30 years, I think. It's really exciting. So quantum mechanics going into chemistry and into biology and explaining all of these things. That's kind of what and again, quantum optics is a great field to understand because it's simple enough, it's accessible to us, and we understand it better than most other things we understand in field theory.
Yeah, thank you. Continue reading and find questions you want to answer. I'm seeing a couple of questions on quantum gates. I'm sure that a lot of people here joined because they know that you work in quantum information, and a lot of people find quantum computers quite interesting. Something I always like to add at the end of talks that kind of touch on that subject, I've had a couple, but I don't think they got recorded, so if you missed them, I'm sorry, is that IBM not only has quantum computers, they also make some of them accessible to the public. So yes, you can use them for free online. If you're interested in coding and you kind of find these things interesting, it's really easy way to get into it, even if, you know, your university doesn't offer any courses on it. I'm going to pop a link in the chat.
Excellent. Excellent, very useful. Let me interject actually to say a bit more about it. One of my former students, Libby Heaney, she actually left physics, interestingly enough, and became an artist. I think for a long time she had an artist and a physicist inside her. And unfortunately, I say unfortunately for me, but not for her probably, the artist won over and prevailed in the long run. But actually she still does art inspired by quantum physics. And I can maybe find some of her images that she's produced using, so maybe this is the first piece of genuine quantum art produced by an online quantum computer at IBM, which I think would follow nicely from the link that you will send as well. So people do all sorts of interesting things and applications in this direction.
Something I did a hackathon at IBM once, and the topic of my group was we made images, and then we used quantum computers to do Fourier transforms of the images.
Yes.
And then we were curious if like the noise was so high that we could so low that we could still see the image. And of course back then there was I'm sure they're still too noisy. You could definitely tell. But the cool thing is they not only offer real quantum computers but also simulated ones that have less noise. So you can do all kinds of fun things.
And it's great that anyone, yeah, as you said, anyone can create an account and you can run whatever sequence of gates. It's fantastic, actually.
Yeah, what was her name again?
Libby Heaney. She is at, I think she's quite independent. She's taught at various London institutions like Goldsmiths College, I think Royal College of Art and so on. But I think what she really does is comes up with all sorts of installations and exhibitions that are ultimately made to communicate how science, and in particular quantum physics, I think really works. And I think if you feel like it, even get in touch with her, because she's always looking for more physicists to engage with and so on. It's fantastic, I think.
Yeah, B, everyone take the initiative. Yeah.
Yes, I'm just reading a few more comments. I don't know if you want me to say, there was one question about this infinite amount of information that's required. And so I'm sorry, like I said, I was kind of trying to speak at a very accessible level, and that means you end up always cutting corners, and I'm always in a kind of deeply unhappy state every time I communicate, because I'm thinking I could have done something better and differently and so on. Here, the simple thing is that when you are summing up all sorts of quantities like the ones that I showed, you are ultimately integrating over continuous variables. So your x, y, and z are continuous. And actually, this almost invariably leads you to these infinities that keep popping up in quantum field theories. And we don't really know how to get rid of them. And mathematically, people frequently say, let's assume a cutoff. Let's assume that there is the smallest distance of space. And then let's assume an upper cutoff, which would be maybe the size of the universe. There is the largest distance of space. And when you do something like this, you can regulate these integrals and they will become finite. Then you have to worry about what they're telling you and so on. But these cutoffs are usually very arbitrary. They are not experimentally motivated, if you like. But the intuition is clear that requiring continuum to specify these things seems to give us lots of problems. And it's not even clear what this corresponds to in reality. And there are all sorts of bounds, like the Bekenstein bound out there, that seem to suggest that a finite volume, which has a finite energy, should also have a finite number of states inside, rather than a continuum. So we have snippets of results from quantum and gravity that tell us that probably space-time is discrete at some level, but we have no idea how to go about this. So that's all I had in mind there.
Yeah, I don't feel like you need to answer all of them. We got quite a few questions and we've been here for quite a while. But if there's anything you want to answer, do look through it. Someone was asking about your research. I'm going to pop a link to your Google Scholar profile in the chat.
Yes, I think Google Scholar is the easiest one. My web pages might be slightly out of date, but they will describe at least the basics of what we are doing on the theory side, as well as experiments. And also, drop me an email and I can send you. This really depends on you, how far you want to go into the field. So already, for instance, in a couple of weeks' time, I think my fourth-year lectures on quantum optics will be available. And I think all of these things that I did very superficially here, I will probably try to do in a bit more detail. When I quantize the field, I will go through all the steps and things like that. So I think if you're interested, you can simply just tune in and access the C2 course in a couple of weeks' time, and it will give you a lot more information about quantum optics. So that's one way to go maybe as well. Oh, am I? Yes. I'm always looking for. I'm one of those people that never advertises any projects on my web pages, and that's because I probably end up having too many applicants anyway. But I'm always interested in having great and motivated young researchers in my group, and so people are always welcome to apply. My style of supervision is possibly more Zen than Western, in the sense that it's a kind of supervision with no supervision, if you see what I mean. Everyone in the group is equal. We don't have a hierarchy, and I don't see this relationship as a boss and employee relationship. It's more like colleagues discussing stuff together. So the only thing I encourage is really independence. That's what I'm looking for, some kind of independence, and I think that's what the PhD ultimately is. Really, it's a kind of license that you can do your own independent research. But I think if you like these kind of topics, anything related to quantum mechanics, it's possible to do within my own group.
That's great. I just want to add, I'm sure that there are a couple of people in the audience right now who are considering PhDs in general. We have a talk tomorrow evening at 8. It's a PhD student, and he'll be talking about what it's like to be a PhD student, to be one in Oxford. And he'll also be talking about his neutrino experiment that he's working on. It's the Dune one, the one at CERN. So come back if you want to ask questions to them. I'll also be there. I'm also doing a PhD, although I have left physics, which I'm trying to redeem myself by being here. So come tomorrow if you have questions about that. It can be quite intimidating. So just wanted to advertise that again.
Yes, I agree. It's a big step. I think that's maybe the main message, that it's hard getting out of this, because the way that we are educated is in a very passive way usually. Whereas with your PhD, you're suddenly expected to become fully independent. In fact, you are meant to find your own problems even. So of course you discuss them with your colleagues, but ultimately it's you who has to identify and say, this sounds like a really exciting thing to look into. And then of course you are ultimately expected to answer that, to make a really original contribution to science. And I think this is a big jump from, from high school and even university education. And I think it's worth thinking about it and talking to others. If you want to, maybe the best way is exactly as you were suggesting, talk to current PhD students, ask them about their own experiences. I'm also happy to put you in touch with my own PhD students. You can talk to them behind my back as well, and then maybe they will tell you how it is. They can complain about me if they don't like the style and so on. And I think it's good discovering these things before you embark on a big step like this.
Yeah, so come along tomorrow. We also have a chess tournament on Saturday in case anyone wants anything social to do. I just wanted to pop that out as well. So we've been here for 1.5 hours. Thank you so much. Someone was asking about your notes. I think they'll be on Canvas. They might be on your webpage, I guess.
They will be on Canvas for sure. And I think, I don't know, how do they do this access? Do they really allow can everyone gain access to this, to any course, or how does that work?
No, someone was just saying that they're quite walled off, but I'm sure that if you send an email, you can get them as well.
I think so. Just send an email. Either Hannah or someone will definitely assist you, because I honestly don't understand why this should be guarded in any secretive way. For all that I care, I think they should stick them out on YouTube, exactly as you are doing, right? That there could be a channel there, and I think it should be public. There shouldn't be any secrecy about it. So yes, I'll make sure that's the case, and there will be literature there as well. I will put a few PDFs of relevant books, papers, and so on, so you can have the full notes.
Great. Well, thank you so much. This was a great talk. Thank you for everyone coming. I know a lot of people had to leave while we were doing the questions. It was a long talk, but for the people who stuck around until the end, thank you for your attention. It's always great to get your questions. And
thanks a lot.
Lots of thanks in the chat.
My pleasure. Just call me anytime. Like I said, I like talking about it, so there's no problem.
Awesome. Thank you.
Great. Take care.
Bye, everyone.
Bye. Bye, everyone.
Bye.